There. Welcome back. Thank you, everyone, for braving the cold to be here. We have our Zoom crew here, more numerous than usual. They're braving the cold in their own places, but thank you for joining us wherever you are in the world here. Let's see, announcements to start with. Your second formative assessment is ready. That is available in Icon. That's the thing you get 2 points for just for filling it out. It's a way of giving structured review. If you could please complete that by Monday night, that way I can look the answers over on Tuesday and we can talk about it as a group. Again, that is in Icon. I also posted your second homework. That is now available. After today, you will be able to do at least the first part of it. It is due 2 weeks from yesterday. I moved the initial due date to be the 26th from the 24th. That way make sure that we have 3 full classes before that material is ready for assessment. And looks like everybody finished their first homework. So yay, exactly. The beginning learning a new language is never easy. So how many of you have attempted to learn a foreign language before in your lives? All of you. Well, guess what? You can add a third to that list because speaking SAS or speaking Stata is like speaking a foreign language. And at this point, I think we know just enough to be like, ¿Dónde está el baño? Right? Where is the bathroom? Could anyone say that in another language for me? Yeah? Excellent. Yes. So that's where we're at. We have the basics. Oh, you know it too? Oh, and and ASL? Yes. One of the most essential phrases in any language, right? Where is the bathroom? So that's where we're at here. Oh, I think one of the Zoomers wants to participate. Let's see what their language. Wo ist die Toilette? Does that mean murdering German? Anyone can someone do that better?
Wait.
Yeah.
German.
No. I don't want to put you on the spot. She's like, no, I'm eating lunch. I'm not doing this right now at school. But you get the idea. We've learned how to ask where the toilet is, basically, in SAS and Stata. But we will get there because it's like learning a foreign language. It doesn't come instinctively. So that's one of the things that we have to do today. I wanted to share with you, Jose last time mentioned in class there was apparently a lawsuit pending against Subway because someone had a foot-long sandwich that only measured 11 inches. And this person took to the internet to throw a fit, as one does. And apparently it actually did turn into this thing. I found a record of it. The U.S. State Court of Appeals 7th Circuit regarding Subway. So if we approach this from a scientific point of view, right? How many foot-long Subway sandwiches do you think they sell in like any given day? Like, I have no idea. Thousands at least, right? A lot. Or any other sandwich company, right, for that matter. They all have various sizes. If one person finds one sandwich to be deficient, how much faith do we have that that one sandwich is characteristic of an entire brand? Not a lot, right? I wouldn't think so. And so that was the initial belief here. I read this story. It turns out that they went ahead and did do an actual study. So they went through and they measured, instead of where the bread ended up, they measured the amount of dough that was supposed to create the bread because there's various baking anomalies that can make things be non-uniform. And it looked like everything was on the up and up, and so they dismissed the lawsuit. So logic prevails in this case. They capped the fees at $525,000 to determine this important information. Yeah. So in terms of science here, right, we don't believe any one sandwich. The lowest level of faith that we could provide is to collect a sample of sandwiches, right? Ideally, we would want to do that many, many, many times. So I talked a hypothetical example about Mountain Dew cans, right? Same premise. And I realized as I was thinking about class and teaching and whatnot, while I was trying to fall asleep, as one does, that in my haste to demonstrate things in Excel, I actually used the wrong formula. If you know if you know the variance from the sample, you're supposed to use n-1 instead of n. Oops, my bad. But you know what that just proves? that people are bad at computing. That's why I want to teach you how to get the computers to do it, because they are programmed to not make such sloppy mistakes. So I thought that might be a nice segue here into the idea of taking a sample, finding a statistic that characterizes the sample like a mean, and trying to determine how close that sample mean is to the mean that it is supposed to be. That's the thing that we were talking about at the end of the day. And we can do that by giving the sample mean a confidence interval, and also doing a significance test, as we're going to call it, of that mean against some other number. So I showed you an example of this from an actual published study, the idea of a twinning effect. Do you remember that? Maybe? A little bit? Let me turn this on to presentation mode. It feels really bright. There we go. There. Doesn't that look nicer? Make it all cozy in here. The question behind this analysis was whether or not the sample means from this sample of twins were significantly lower than what the population means for these standardized tests said they should be. And in this one example of PPVT vocabulary, which I also mislabeled, I realized that is, I believe, receptive vocabulary. Does anyone want to correct me? They have to point at a picture. They don't have to say anything. So it's a different type of vocabulary, not productive. But anywho, in this example, at age 4, the twins had means of 96 and 93 on a test that they were supposed to have means of 100. By age 6, their means looked closer to the hundreds they were supposed to be. And so we interpreted this as, yes, there is evidence for a twinning effect, and that twinning effect somewhat diminishes or goes away by the time they're 6 years old. And so how do I know whether or not these numbers are different enough from the 100 that they were supposed to be? And the key to knowing this lies in the standard error. So the standard error tells you how far off the sample mean is from the population mean. We use that standard error to build a confidence interval. That describes if we did the same sampling procedure over and over and over again, X% of the time we would find the population mean in that interval. And we get to decide what X is. Traditionally, it's a 95% confidence interval. In that case, you would pick a number that corresponds to that. This is from a Z distribution, and you make an interval. You can also decide how likely it is that you would see a sample mean like this if the population mean were accurate. And so the next slide then, this is slide 14, shows an example of how to do that. And so your test statistic, either Z or T, that's the thing that gives you a location on the curve. So sampling distributions like this, probability distributions, their job is to tell you for any observed value how likely it is. And this is a standardized way of taking means on any scale and standard errors on any scale and translating them into something that we readily know what it means. And so the first one that we saw, this is our friend standard normal, otherwise known as Z. And according to this distribution, which is supposed to characterize sample means pretty well, the sample mean, any value within plus or minus 1 standard deviation happens about 68% of the time. Plus or minus 2 happens about 95% of the time. And so we can think about that with respect to individuals relative to a sample mean, and we can also think about that with respect to sample means relative to population means. It works the same way. And so if we have this type of curve here, and we located this test on that curve as a Z of 0.35. So the location is given to you as the sample mean minus the population mean it was supposed to be divided by the sample standard error. That thing works out to a Z test statistic, of 0.35. So that is almost smack in the middle of the distribution. Meaning that's well within expected territory. If the true mean were 100, we would see a mean of 100 and point whatever a lot of the time. The other one that we looked at was the third one here. This mean is actually way above what it's supposed to be. And how much above? It translates into a z of 4. 4 standard deviations above the mean. That is a probability that's super tiny, 0.0018. So yeah, if the sample mean were 100, and this is our best guess at the average deviation of anyone, I'm saying this backwards, if the population mean, thank you, were 100. I have mom brain, I'm sorry. I spent the morning with my son and I'm having trouble making the transition. If you want to talk about Mickey Mouse racers or Paw Patrol or play soccer in the basement, that's what I've been doing today. So give me a moment to just like put on the other hat. Right? When he was 2, he used to call me Dr. Mommy all the time. And it was funny because we tried to tell him that his dad was a doctor too, and he was not having it. He's like, Dr. Mommy. And I thought that was like the most perfect summary of my life, right? I am Dr. Mommy. Like, I have 2 different heads and I have to switch between them. So, sorry, I'm having trouble making the transition. Let's try this again. If the population mean were 100, then we would not see a sample mean this extreme of 101.93 very often. It's way out in unexpected land on the high side. That's because this standard error is so small. We have a lot of faith that our sample mean shouldn't wiggle much around the population mean. There's not a lot of wiggle. So this is like 4 wiggles away, 4 standard errors, if you will. And in this sample of a lot of people here, as you can see, the z distribution to make this type of test works just fine. In smaller samples, it doesn't work just fine. Then we need a shape that looks very similar, but it's squished down, it's flatter, and that's our friend t. If you have enough people, t and z are the same thing. So almost exclusively in the rest of this class, we'll talk about t. But it's the same idea. It's a way of taking any statistic and the standard error for that statistic, so we only know one so far, the mean, but we'll see others, and placing it on a scale of expectedness where the scale itself is generic. We know what a t of 2 means. We know what a t of 4 means. So it tells us if what we believe is true is actually true, then how likely is it that we saw what we saw from our one sample? In terms of science, you could interpret this significant result here, this 101.93 being way unexpected relative to 100 in one of 2 ways. You could say, wow, those 6-year-old twins happen to be really, really smart. Or you could say, excuse me, the population mean is not really 100. The subway argument. Which is it?
Doesn't that test have a huge sample? I mean, like they've done repetitions and all the data goes together.
Well, this is one sample.
But but the 100 that we get from all the other samples being put together has a lot of, what do I call that?
Evidence? Replication?
Evidence. Replication. Has had many replications, so I think 100 is probably
well, that's what the makers of the PPDT test would like to argue, right? They publish tests that have been subject to a lot of scrutiny. They collect a lot of data to be able to make this assertion. Carly, were you going to say something?
No, I was just pointing towards the second option.
The second option? Yeah. So that's what the subway argument was trying to make, right? He had one sandwich, which says nothing. But even if he had one sample of 100 sandwiches, he was trying to argue that the population mean was wrong because he got a different sample mean. Can't argue that unless you have more than one sample mean at a minimum, right? If you collected enough sample means, then you would have evidence that maybe the population mean isn't what it's supposed to be. But any one sample can't tell you a whole lot. So, all right. Any questions from the Zoomers so far? Any questions from the non-Zoomers so far? No. So do you want to see how to make SAS and Stata give us this type of stuff?
Absolutely.
Absolutely. Thank you for your enthusiasm. I appreciate that.
It's so espresso being the meeting.
Espresso beans. So that is a chemically enhanced enthusiasm, as it were. Yeah, I've already had too much coffee today. I'm having placebo do right now. Because there's a caffeine arousal curve, right? Like you hit the top of the curve and you keep drinking caffeine and then it's like, I'm shaky and stuttery and this is not working. That's kind of what I'm feeling like right now. I got to calm it down. So let's look at example 2. We'll learn some more phrases besides "Donde está el baño?" So I've borrowed a data set that is a subsample of the one that's used in the Mitchell textbook. This is from the General Social Survey in 2012. That survey is actually humongous. It has thousands and thousands of people. The data set that is along with this textbook shortened it to about 1,000 or so. I further shortened it into a subsample of 100, just so that we would have smaller cases to visualize and play with. If you want to see how I built this handout, you can, but you don't have to. Inside the example 2 folder that's posted on the course website, it was example 2 SAS and Stata files. That has the original data set, the syntax in both programs, as well as the output that is generated from the syntax. So if you're the kind of person who likes to run it and see it and that makes you feel good, great, you can do that. What I would prefer to do with our time is to try to navigate through the syntax, talk about what it means, how you would manipulate it to do what you want it to do, and then show you what the output looks like, where to find the information that actually answers your questions, and interpret it correctly.
And you said Word doc is in that folder?
The Word doc is not. I put a PDF on the website that is right here, example 2. That way all of my formatting stays nice and clean. Because the dirty little secret about these programs is that they are happy to do whatever you ask them to, even if that makes no sense whatsoever. So trying to make sure that we're asking for things that make sense, as well as knowing what comes out and what to do with it, that's the objective. Okay. So first things first, we have to import the data into the program. It turns out that SAS lets you import directly far more different types of files than Stata does. So I read a Stata formatted data set into Stata, and I also read the same data set into SAS. So we have SAS syntax right here. This little chunk is doing 2 things. First off, I guess it's technically 3. It's telling SAS where the folder is that contains the files that we want to work with. So file save, this thing right here, that's an abbreviation. Elsewhere in the syntax, anytime that you see this combination, ampersand, the name of the abbreviation, and then a period, it's like, oh, take that abbreviation and fill it in here. So proc import is how you get any kind of data set into SAS that is not a native SAS data set. After you tell it where the data set is, there's a slash, and then you tell it the name of the data set. This data set was called GSS subsample. It is a DTA extension. That's the Stata file format. It is going to the work library in SAS, which is a generic directory that dies at the end of your session, and it's being called example 2. This thing right here, DBMS, that stands for Database Management System. That's an internal set of commands that tell it how to interpret the information in the file. They have DBMS systems for Excel, for SPSS data, for Stata data, for Access, for any kind of data set that you might have. And the last thing, replace, means if this data file already is in SAS, go ahead and write over it. Now this seems like it might be a bad idea, right? Write over data is bad. However, write over which data is the question. Your original data is safe and sound in its data format. What I'm telling it is okay to write over is this data set in SAS format in the temporary library. The reason that you might want to do this Let's say that you attempt to make a new variable and end up deleting a variable instead, overwriting some information. Been there, done that, wore the t-shirt. You can re-import and start over again this way. So it's a good idea to have this, that way you can rerun your whole syntax and not have it yell at you. This same file save abbreviation is being used in this command right here. ODS stands for Output Delivery System. It is starting a rich text format document, something that you can view in Word, to send your output to. That way you don't have to rerun SAS every time you want to look at your results. You can save a copy of it. And that's helpful if you need to share results with your colleagues or just for your own sanity to make sure that you don't lose it. Okay, so SAS folks, any questions on those three pieces? Okay. Stata folks, same exact three commands, Stata flavor. So global file save here is doing the exact same thing as let file save in SAS. It is defining an abbreviation. Note that you have quotes in Stata to do this. The $sign rather than the ampersand is then invoking that abbreviation to fill in here. Use is the same thing as import if the data set is already in Stata format. Clear is the same idea as replace. It means that you can start over again if you want to re-import. And log means create a plain text file to send the results to. That way you have a record of what you've done in Stata as well. And replace means go ahead and make it again if you've already started it and you want to do so. Okay. So you've seen all three of these commands in Homework 1. You'll continue to see them in each other example and each other homework. In terms of language, both programs have comments. You will see that in all of the examples that I give you, I have comments above the commands to say what it's supposed to be doing. You know it's a comment if it begins with a star. Everything in SAS ends with a semicolon at the end of each phrase. In Stata, you can use stars or you can use 2 slashes like that. I'm using 2 slashes so that the differences between the programs are a little more salient. But note that there are no semicolons ending any of these phrases. Stata thinks that you're done if the line finishes. So it goes to the end of the line and it cuts you off, whether or not you're done. It just assumes you are. We'll see examples of how to make it continue in just a second. Okay. Labeling and making variables, that's the next step. So proc format in SAS is a way that you can attach text labels to the numeric values in a categorical variable. So I'm defining these formats as they are. They're pieces of information that I will attach to the data set. One is going to be for a variable for binary gender. The same variable coded backwards, we'll see why that is in just a minute. And for marital status. Those are 3 of the variables we're going to play with today. In here is an example of how we would make new variables if needed. So we talked about linear transformations before. Do you remember that? Maybe? Linear transformations of variables? Yes? When would you do that? Or why would you do that? Either question. No? Not that? You remember we were talking about it though.
It sounds familiar.
It sounds familiar.
Sure it's when it just kind of moves over.
Yes, that. I will accept gestures, always. You're taking your scale and just either moving it over. So if you're subtracting a mean, that is called centering. That's one particular type of transformation. Another one that we talked about is z-scoring. So that's where you take a variable and you standardize it to a mean 0 and variance 1. The reason that you would do z-scoring is to put multiple variables on the same metric so that you can compare their associations more easily. There's a couple of linear and nonlinear transformations in here that I did just to sort of show you what happens in practice as you look at relationships of these variables with others. That's the next part of the things we're going to do. So for instance, making a new variable via linear transformation in SAS would go something like this. I have a variable that's called family income. The original variable is right here, fam inc. it's scaled in dollars. To make the numbers a little more manageable, I'm dividing that variable by 1,000 and creating a new one. So the way that you interpret this type of statement is new equals, and then how do you want to make it? So it's new equals the old one divided by 1,000 in this case, semicolon to finish the thought. And then the label. So that attaches, the variable column itself is now called FAMINC1000 that I just made. The text that's in this pinky purple color here, that is a variable label. So if you want to refer to the column, tell SAS to summarize it, to use it in an analysis of any kind, you refer to the name. The purpose of the label is to print next to the name on the output so that your output is easier to read. In very large data sets, you can end up with variables called things like x cubed p4. And you might know what that meant at one point in time, but you may not remember it at some time later. Or if you need to share the data set with someone, they may not know what that means. The labels are like your Orphan Annie decoder ring that allows you to translate back into what the actual information means. So the format of a label statement, name equals you thing that you want to attach to it as extra information in the quotes. A nonlinear transformation, like a natural log transformation, would look like this. SAS, Stata, and all other stats programs have built-in numeric functions that know how to do things. Taking the natural log is one of them. The natural log of something that's 0 is undefined, so I added 1 just in case there's any families in our data set without any family income. And so the new variable is called FAMINC_log. So relative to FAMINC1000, FAMINC_log is exactly the same thing or not quite? So if I take FAMINC and I divide by 1,000, that's a linear transformation. I'm just shifting the scale. If I take FAMINC and I do a natural log transformation of it, am I just shifting the scale or am I doing something else?
You're also transforming it.
Transforming it non-linearly to the log takes a special shape. Let me show you the picture again that goes with this. Come on. That one. This is slide 3 in lecture 2. Log transforms are often used on variables that are positively skewed because what they do is take the extreme positive values and shove them in, reduce the skewness, and at the same time they take the very small values and spread them out on the negative side. In models for count outcomes, for example, one of the things that's built into the model is a natural log transform so that the counts that are predicted by the model stay above 0. So you see logs a lot, but the key thing that I'm trying to illustrate here is that it's a non-linear transformation. It's not just a shifting over of the information. It changes the relative distances between the values. The values on the positive end are closer together than they would be under the original data. If I want to make a z-score, in SAS that's a separate command, so I'm making a copy of the FAMINC variable, calling it with a z on the end here. I'm going to z-score that in just a minute. And one other thing that I'm going to do here, for reasons that will become clear probably next class, is rename a variable in the data set that's called female. So in a lot of data sets, including this one, there is a convention when you have a binary variable. So one group is a 0 and one group is a 1. You name the variable after the group that's the 1. So like female in this data set means is female, and 1 equals yes and 0 equals no. That gets really confusing when one of the values of your variable itself is female, because then you can't tell if you're referring to the name of a variable or the value of one level of the variable. So I renamed this thing male 0, female 1, because that's what it is. Likewise, there's a variable called married. that I renamed to be, I made a copy of it rather, unmarried 0, married 1. So that will help us later on in the output differentiate what is a value of a variable versus the name of the variable. And then last but not least, attaching the formats to this. In SAS, making a z-score happens with a procedure called proc standard. Data equals, just like any of the other procs, tells it which data set you want to do this to. Unlike the other procs that you've seen, it's going to save the results in a new data set if you want. And so I'm saying, no, go ahead and put them in the same one, it's fine. Mean and standard deviation give you options as to how you want to standardize it. Z-scores is one option. You might also come across T-scores. Have you heard of those? T-scores is mean 10, standard deviation 15, is that right? I'd have to look it up. What is T-score? Remember? No, remember? It's another standardization scheme. It shows up every now and again. Z-scores are far more common though. And so now that FAM-Inc. Z variable is going to be Z-scored as we requested. So the one thing that trips people up more than anything else in SAS in making new variables, you cannot ask it to make anything related to new variables, labels, or anything in open code. Because SAS allows you to have multiple data sets open at the same time, anything you do you have to tell it which data set you want to do it to. So this combination right here that I have highlighted, data and set, this is a fancy way of saying save as itself. The data part, this means make me a new data set, put it in the work library, call it example 2. The set means from. Where do we want to make the new data set out of? Oh, from the one in the work library, also called example 2. So this is saving it as itself. So it's taking the original data set, adding all of these new variables that we requested to it, and then saving it with the same name. Anytime that you make new variables, you have to have data and set at the top to tell it where the new variables are supposed to go and where the old variables are that the new variables are being made from. And you also have to finish with a run. Run is like saying please. Stata is different that way. Stata only allows you to have one data set open at a time. So you don't have to tell it which data set to do things to because it's that one. Yes, sir.
Can I ask something really basic?
I love basic.
So where I'm struggling is really, I got this part, it's fine. Is it in the command window where we put it in? Where do we actually put it in?
Great question. In Stata, there are 2 potential places to put it in. Let me see if I have enough bandwidth to open up Stata real quick. I have it on this computer. There it is. There we go. No, I don't need updates, thank you. So I think your question is, do we type things down here, or do we type them somewhere else?
Exactly right.
Okay.
And I tried down there and it didn't go.
Yeah, in SAS, there is no down there. Like, it doesn't give you the choice. There's only one editor window where the typing goes. Let's see. If I want to do file, how did I figure out how to do a new one before? I think that I had a hard time figuring out how to do a new one before, but
That makes 2 of us.
yeah, I thought that's why I always give you one. I can tell you that to start with. So if I have, for example, homework 1 due. Oh no, that's right. The due executes it. If I go through, I can go through here first and open it inside Stata. Open. The default is data files, but you can ask it to find due files. So let me find, for example, example 1 from Stata. All right, it opens up in a separate place. Now, what are the relative merits of typing in either place? Because the short answer is that you can use either. you can take these types of commands, like I have here in this data code, and put them in this window. The problem with doing that is that you lose it the second you replace it with something else. It is not a cumulative record of what you've done. That is bad for two reasons. It's bad in terms of reproducibility. Like if you had to show somebody a record of all the steps you took in an analysis to write a results section or something like that, you don't have that record. The other thing is that you have to reinvent the wheel. Every time you want to do something that was like something you did before, the way that I do it is to open up something like I did before and copy it and start messing with it because I don't want to have to type everything from scratch. So if you break the habit of typing in this window and instead type over here and then highlight it and run it, then you'll have this full record to serve as a template for other things and to serve as documentation.
Thank you.
You're welcome. Thanks for the question. And no, that's not basic. SAS doesn't give you that choice. There's only one window to type in. And so you save the syntax file and that's what happens. Okay. Other questions? So the same ideas in Stata. If SAS is French, Stata is like Italian. I mean, there's a lot of things that are related. They sort of sound the same. Or excuse me, I was going to say Spanish and Italian, not French and Italian. Label define is how you make variable labels. So these are the values that get attached to the categories. That is the same thing as proc format. Gen is how you make a new variable. So the code to make new variables in Stata looks exactly the same as it does in SAS, minus this gen. Gen stands for generate, and no semicolon at the end. Label variable, can you guess what that does? Yeah, labels the variable. Note that everything that's Stata commands are in lowercase. It insists. You can make a log transform version, label that. If you have to use a more complicated function, such as to make a z-score, that's egen. I have yet to figure out the technical definition of what gen versus egen is, but I think of egen as the more complicated version of gen. If I try to do something and I type gen and it doesn't work, I usually stick an e in front of it, and 99 times out of 100 it will work. So that's my my first-hand Stata knowledge that I acquired by brute force. I don't think it works like that. I think it will yell at you. Gen is nested in egen, but like they're for different things. I just haven't ever seen a technical definition of what the difference is. I just know egen is fancier. It has functions built in that are not just like arithmetic transformations. So z-scoring is accomplished by this std function. And yes, go ahead and giggle. My other class did. It's an unfortunate abbreviation. Gen, making new variables, labeling, attaching. So, in your next homework, you'll get a chance to practice a little bit of this. I think you'll have to make maybe one new variable, but I wanted to start getting you used to seeing it because, in all honesty, in analysis, probably 70 to 80% of your time is going to be spent setting up your data set to do what you want to do. Making sure the variables are in the right format, making sure that they are scaled correctly, making sure that they have all the information attached to them so that you know what they mean. That stuff takes time. So I want to expose you to the reality of that process. Okay. So how to actually get information. So this is reviewing what you got to do in homework 1, proc means. Let's summarize the new variables that we created. What does proc means do? Gives you means. More generally, for what kind of variable would you like to use proc means? What are the two main kinds of variables?
Nominal?
Nominal is a very specific kind of one of the two. Categorical and yeah, so under categorical is binary, ordinal, nominal. And the other one? Yeah, numbers, right? Yeah, quantitative. Yeah, so proc means is for summarizing quantitative variables. It provides characteristics like central tendency, dispersion, minimum, maximum, stuff like that. Proc univariate gives all of those things plus a whole lot more. So proc univariate is the more extensive version of proc means. I have proc means here for all the various versions of family income that we made. So you can see the relationship between the first two. Family income is the original variable. Family income with 1,000 attached to the name is divided by 1,000. So we took the decimal point and shoved it over 3 places. That is how it should be. So that's a linear transformation. Family Inc. Z has a mean of exactly 100 and a standard deviation of 1. Coincidence or not? Yeah, we made it as a z-score.
Right.
We told it to do that. We told it to rescale itself such that it has a mean of 0 and a standard deviation of 1. Last but not least, the log of family income has a mean of 10, standard deviation of 1. So that is nonlinear transformation. That's in a log scale. If you want to see what these new variables look like, proc univariate here is what I use to make pictures. Var in each of these procs means and univariate stands for variable. That's where you type the names of the columns that you want the information about. Histogram makes a picture where you get to decide what the bins are that rounds these quantitative variables into convenient increments, and if you don't decide, it does it for you. So if we look at these 4 histograms, let me shrink them so you can see them all at the same time. One of these things is not like the other. Which is the oddball? Yeah.
Oh,
Yeah, this is the only one. The 3 of these are completely the same variable. They're just linear transformations on the different scale. Log is the one that's different. Now note, family income z-score is the one that's right here in the lower left-hand corner. Making it a z-score did not make it normally distributed. So z gets thrown around a lot. It's important to make a distinction between z as in the standard normal picture. That is that picture versus a z-score of an observed variable, which does not make it look like that. It just translates the observed variable into having a mean of 0 and a standard deviation of 1. It does not make it perfectly normally distributed. But that's okay, because it's not about the shape of the variable. It's about the distribution of the sample means from the variable. Once you have enough people, the sampling distribution of those means is normal, and that's when we do tests involving z and t, that's what we're going for. Okay. Stata folks, the analog to proc means summarize. Now I added something here to help control the output. In SAS, I asked for 3 digits after the decimal so that the table was a little bit easier to read. That's a choice you can make for whatever works for you. The analog to that in Stata is that format statement before it, and then invoking a format option. Options are after the commas in Stata. That way it uses that format of the variables. So here's the analog of the output for proc means. It gives you the n, the mean, standard deviation, min and max. It doesn't give you variance. There are 2 ways that you can use this information to get variance. One is to get your calculator out, enter this number, and do what to it to get variance? Oh, square root it or square it? Yeah, this was a homework question.
Square root it.
So I have standard deviation. I want variance.
Squared it.
Square it. So you can get your calculator out, square that number, or you add 1 extra command option to get a whole bunch of other information, including the variance. So. Stata will also make histograms. Unfortunately, they pop out in separate windows. They don't go to your main log file, so I didn't show them here. So this is, the only new thing so far is just the idea of making new variables and labeling them, which you've seen examples of in homework 1. You've seen proc means and you've seen proc univariate and summarize. And now here's something new. So before we see something new, any questions about the old stuff? Relatively old, like a week old. Okay. Then let's see something new. Proc t-test. Oh, question from the Zoomers? Let me see what we got. Proc univariate. Proc univariate does the same thing as proc means, but it gives more descriptive statistics like percentiles and medians and stuff. And it is analogous to the summarize command in Stata when you add the detail option. Does that work? All right. Yep, just making sure. Great. Yep, you got it. So this is your very first stats test. Remember, there's two kinds of stats, right? Descriptive and inferential. All we've had so far is descriptive. The homework that you just completed was functionally a method section, right? Describing your sample and your variables. This would be your first example of an inferential test. How would you determine if your sample mean is different than the mean it was supposed to be? So this is predicated on the idea that you know what your population mean was supposed to be. You have that as an endpoint. So this is the example that we saw with the twinning and with the Mountain Dew cans. So first, always, which data set do you want to use in SAS? For var, that stands for variable. Which variable do you want to use? I'm picking a variable for education here. And I want to know if the education level in my sample, on average, this is years of education, is significantly different from a high school degree. That's my question. I have reason to believe that it should be 12 years of education, and I want to find out if this subsample is different than that. Yeah, this is going to be called the null hypothesis. We haven't introduced that yet, but it's the idea of what do you expect? What's your guess for what you're trying to compare against? Sides equals 2. Can you guess what that refers to?
Two-tailed test.
Two-tailed or one-tailed, what's the difference? Besides one-tailed being voodoo and two-tailed being okay, but you're going to say? You can always use two. Well, not always, but most of the time. What's the difference? Here, let me pull up a picture, because I think that will help. This picture. This is slide 12.
Confidence interval?
What about the confidence interval?
If you're running a two-tailed test, you can, that's on the tip of my tongue too.
Yeah, you can
Yeah,
phone a
have
friend if you
positive
want.
Yeah, you can have like, anybody want to chime in?
Yeah, you can phone a friend. That's fine.
You can have like plus or minus, it can be
Right.
go either way.
Yes, exactly. Plus or minus can go either way. I take the gestures, yes. Because you know what you mean, right? It's like tying the words to the idea. Yeah. It's that if something is unexpected, you are willing to entertain the possibility that it is unexpectedly too big or unexpectedly too small. Either of those is noteworthy. So the way that that is going to be phrased, in this case, as a two-tailed test is, I think the sample mean should be 12. If it's not 12, it's different than 12. Right? I'm not saying greater, I'm not saying less, or different. And if it's different low, that's noteworthy. If it's different high, that's noteworthy. That's what two-tailed is. The only instance I can think of in which one-tailed makes sense is if the other side is impossible. Like if you're testing a variance. A variance is either 0 or greater than 0. Likewise, when we get into models and we talk about variance accounted for by the model, it's either 0 or greater than 0. There's very few instances in which you don't have the other direction be possible. If it's possible to have it both ways, then it should be a two-tailed test. Alpha. Back to the picture. What's alpha?
Is that the part in the middle or the part in the tail?
Oh, good question. It's either the part in the middle or the part in the tails.
It's part in the middle.
Oh, but we got two votes. What if I told you that alpha is a synonym for aberrant?
Tail.
Tail. Yeah, aberrant is alpha.
Okay.
Alpha is the unexpected. Expected is the confidence interval. So if I have a 90% confidence interval where I'm defining where unexpected versus expected is, it's 90% is the expected region. If it's outside of that, that's unexpected, that's aberrant, that's alpha. Okay. Yep. So I am telling it that I want an alpha of 0.05. That means I want to set it up so that only 5% of the time I would see something that extreme if 12 were really the population mean. And CI equal also does what? See, I didn't even remember that off the top of my head. I'm glad I wrote a note to myself. CI equal also requests the CI for SD. What does that mean? CI is a synonym for, or abbreviation for,
Confidence interval.
confidence interval. You will also see that as CL, by the way, confidence limit. For SD, SD means what?
Standard deviation.
Standard deviation. So I'm saying this is also going to give me a confidence interval around the standard deviation, in case I cared about that. Okay. The analogous data code. Let me see if I can shrink this so I can show both of these commands at the same time. No, almost not quite. All right. So at the bottom here, this data, education equals 12. You would think that that's a typo, but no, it's not. Equals is not the same as equals. It's an equivalency. So it's like saying if education is equivalent to 12. It's not saying it's 12. It's known as a conditional logic statement. Now note the way that Stata wants you to determine your alpha is the opposite of alpha. So level 95 means your confidence level, meaning how much area is inside the expected part, whereas alpha is your unconfidence level. That's the new word I made up last time, right? No one told me I couldn't. It's unconfidence. Alpha is unconfidence is 0.05. That means the confidence part, the confidence level is 95. See, fun little tricks like this keep you on your toes, right? CI is a separate command to get confidence intervals for the variance. So I did that for education as well so that we could get all of the same output. Okay, how are we doing so far?
So you need both lines.
You need both lines if you want the confidence interval for the variance as well. That is less common, but it may be something that you care about.
Clarifying, we only have to do this in one of the programs, right? We don't have to do it in both.
No, but you know what you would get if you did it in both?
A++.
What?
A++.
A++? Not exactly.
Something else to put on your Vita.
Something else to put on your Vita. Plus, every time you learn a new stats language, it gets easier and easier. So yes, if you're looking for a challenge, if you have some spare time that you'd like to fill, for example, or you just think this stuff is really cool and you like being, quant cool like me, I'm a giant nerd and I'm okay with that. I know my place in life, and look, I have a job because I love this stuff so much, right? So yeah, if you have extra time to kill, learn both programs. And if you still have more time to kill, go do it in R, because R runs the world now. The more programs you know, the more lines on your CV, the more potential collaborators you have who only know one package, because then you can speak their language in their package. So yeah, only one at a minimum.
Okay.
But if you're up for the challenge, more than one. The reason that I picked these two packages in particular is because they both have a lot of room to grow into advanced models. SPSS has less room to grow. So does, Minitab? That's another one that's sort of a basic one. And certainly more than Excel. Excel technically can be used to do statistical analysis, but it has issues with numeric precision. So it's typically not advised to do so in real life. It's fine for like toy examples and pedagogical things and stuff, but yeah. These two programs both have a really high ceiling in terms of the number of things you can do with them. So here's some stuff. So let's go through this. Some of these columns are self-evident. Some of them require a little bit of digestion. Okay, what's N? There it is. Sample size. Yep. N is called obs in Stata, because why not?
Observations
Yeah.
instead of number.
Yep. Like number of observations. That would be the optimal level, right? But nah. Mean? We know what that is, right? The same thing it was in elementary school, as you said before? Yep.
Arithmetic.
Yep. It's the arithmetic mean. There are more than one kind, but there is more than one kind. So mean, cool. Standard deviation is next in SAS. It's 1 over in Stata.
Deviation is within sample.
It's a within sample thing. It is a deviation of what from what?
Individual scores from the mean.
Average deviation of any one person's score from the mean. Average deviation of any one can from the pack mean. Then we have standard error. What's standard error versus standard deviation? Because they sound a lot the same, don't they? Standard deviation squared is not standard error. It is something else. Starts with a V. Variance. Yeah, that's not on here. It reports something else. It reports standard deviation instead of variance. But yeah, if you wanted the variance, that's standard deviation squared. Standard error is standard deviation divided by the square root of n minus 1. Got the minus 1 today, although I forgot it here. There. Problem solved. What's that? Standard error. It's a deviation, but at a higher level of abstraction. Yeah, that. Say it again.
So it's the amount of deviation from the mean when you look at each sample of a whole population.
Yes, it is the average deviation of a given sample mean from the population mean. And yes, we only have one sample of which to say that, but that doesn't stop us.
Because we have faith.
We do. We have faith. Little George Michael for you. So here's my confidence interval. That is roughly two standard errors, around the mean. It's 1.96 in this case is the confidence interval because my sample size is 100. So you have in this slide right here, 17, this is an example of what the number would be that has to multiply the standard error to give you your desired level of confidence based on your sample size. So this table across the top varies your alpha level, which is the opposite of confidence, right? So alpha of 0.05 is 95% confidence. Alpha of 0.025 would be 97.5% confidence. And then down this is degrees of freedom, which right now is sample size minus 1. So that, all that information is already programmed into the procedures.
So you don't have to use a stupid table.
No stupid tables. Tables are useful pedagogically, and they were useful before computers did stuff for you, but they're not useful in practice. So yeah, there's my confidence interval. Now let's look at that. Do you see 12 in there anywhere? Not even close, right? So this is supposed to be the range that the population mean would be in across 95% of the replicated samples. It's not there. So yeah, it looks like we're way off of where it should be. How far off are we? Here's my degrees of freedom for the t, which is 99. Can you guess where 99 came from?
100 minus 1.
100 minus 1. And that's another thing it will figure out for you. T value. So that was calculated by the program as 13.81 minus 12 divided by the standard error. That's in your slides. That works out to be a t of 5. Yes. Correct. Way high. So if we go back to our happy little t table, sort of like happy little trees, but not quite. So t of 2-ish is where you have like 2 standard deviations out, 2 standard errors out in this case. You keep going, 5 is like out here. Way out. Very unexpected. Yeah, it's so we don't know, we can't say that no, the population mean is wrong. All we can say is, yeah, this sample, if the true mean were 12, it'd be very unexpected to find a sample with a mean of 13.8. Very unexpected. How unexpected? It would happen less than 0.0001% of the time. That's the exact probability. SAS stops printing it after 4 decimal places. You will see sort of sloppy reporting in some programs, unfortunately, including Stata. It says things like p equals 0. Can't say that. P is never 0. It's 0 to 4 decimal places. But the information in Stata is exactly the same, albeit slightly rearranged. It has your confidence interval around the sample mean up here. Here is the t value that we saw before with the degrees of freedom. And then down here is an extra line of stuff that did not show up in SAS. Now, what am I to make of this?
Alternative hypothesis.
Yeah, we haven't talked about that yet, but these are the tails, right? So the first one is, what are the chances the mean is less than 12? No chance. The mean is 13. What are the chances that it is?
Exactly
Exclamation point means not.
Oh.
And yes, you have to say it with enthusiasm because it's an exclamation point. Not 12.
Not 12.
And then what are the chances it's greater than 12? So not 12 is two-tailed, willing to accept either high or low. Greater than 12, tail that way. Less than 12, tail that way. So it gives you all 3. In SAS, I had already specified that I wanted 2 tails, so it only gave me 1. And then here's the extra piece of output that has the confidence interval. In Stata, it gives it for the variance. In SAS, it gives it for the standard deviation instead. So if you want to get it for the variance, you can square the standard deviation version. If you have Stata and you want it for the standard deviation, you square root this version. And then last but not least, words. See, this is me shamelessly trying to get you guys to like me and currying favor.
So it just spits that out.
No.
No. Okay. Darn.
If it spit that out, I would not have a job. Are you kidding me? That's a trade secret. No, I spit that out for you. And I will continue to do so for every single thing we do because you have to learn how to write about it.
Mm-hmm.
The good news is that results sections are completely formulaic. The best results section is boring as crap. It is predictable, it is repetitive, and it is clear. Right? We all agree on conventions for how to report things. They vary slightly from field to field, but they all have the same sort of template. And that is exactly how I literally could program in results sections in your homework because it is that formulaic. But you wouldn't know the formula unless someone teaches it to you. So part of being able to ask for this information, know what it is when it pops out, and then try to convey it. It's 3 important steps to being able to actually do an analysis responsibly in practice. So this is how I would have written this up. The extent of unexpected deviation from our sample mean for years of education from a hypothesized population mean was examined using a 1-sample t-test with a 2-tailed alpha level of 0.05. So this is the formula. We found stat, comma, indicating that, put it in English, always. So T, that's the test that we used. What's inside the parentheses here?
Oh, there's no value.
Good guess, but no.
Degrees of freedom.
This is degrees of freedom, equals the T value, and then P less than, that's our P value. What is the probability of observing a T this big, not very high?
P means probability, and PR means probability too.
Yes, it does.
Okay, thanks.
This p-value goes with the t-test statistic. It tells you how much area under the distribution there is outside of that point. Yep. So because we used a 2-tailed test, this p-value area is both more extreme than -5 on this way or more extreme than +5 that way. So it's like plus or minus 5 is the area. Indicating that. So if you are a statistician, that much is sufficient. If you are a real person who wants to learn something about your results, this is the part that your reader is going to highlight. Give it to them. Indicating that the sample mean of 13.81 was significantly larger than the hypothesized mean. This parenthetical is something that I added to clarify that. It's probably too much for an actual journal article. I will always tend to overwrite things for your benefit rather than underwrite them. So yeah, other than Subway or defending your sample against reviewer 3, I can't think of too many cases where you would use this type of test. But given that the only thing we've learned so far is univariate statistics, this is how you would answer a question about a univariate statistic. So if you want to say that your sample is representative of some population, and you know your population is supposed to have a mean of X, someone could jump on you and say, no, your sample looks like it's not representative, that mean is too high. Okay, what's the probability that I would observe my sample if you're right about the mean? How discrepant is it? It's a way to answer that directly, rather than just have an opinion as to whether your sample looks too different. The thing that we get to do next, after we do the sample proportion thing, is start looking at patterns of association between variables and how you would answer questions about those. That's much more useful to know. But we'll do sample proportions next time. Okay, how are we doing? So far, so good? See, this basic concept of, like, what is it? What was it supposed to be? How far off is it sort of from our sample from the population on average, and where do we locate that into some sort of distribution that tells us where expected is? We're going to do that like 8,000 times this semester. Yeah. So you'll see it in lots and lots of special cases, but that's the general concept. So if it's feeling a little shaky because it's new, that's okay. We're going to practice the heck out of it. All right. Questions or comments before we adjourn? All right, then I can say have a good weekend this time, because it is Thursday. Stay safe, stay warm, and finish your formative assessment number 2, and let me know if you need anything, okay? All right.